Welcome to our exploration of the ocean floor. When we look at the surface of the ocean, it appears flat and uniform, but beneath the waves lies a hidden landscape just as complex and dramatic as anything on land. This is known as ocean relief. It is shaped by a combination of tectonic plate movements, volcanic eruptions, and the slow but steady forces of erosion and deposition. Understanding this underwater topography is crucial because these physical features actually control how seawater moves, which in turn affects global climate, marine navigation, and where we find the best fishing grounds. Geographers divide the ocean floor into two broad categories, major and minor relief features. Let us start with the major ones. If you were to walk from the beach straight out into the deep ocean, you would encounter four primary zones. First, the shallow continental shelf, followed by a steep drop-off called the continental slope. At the base of that slope is a gentler incline known as the continental rise, which eventually flattens out into the vast deep-sea plain, or abyssal plain. Let us look closer at the first major feature, the continental shelf. This is essentially the submerged edge of a continent. It is a very gently sloping area, with a gradient of 1 degree or less. Even though it is underwater, it is geologically part of the landmass. The shelf continues until it reaches a sudden, steep drop-off, known as the shelf break. While they only cover about 7.5% of the ocean's total area, these shallow seas and gulfs are incredibly significant. You might wonder how these submerged shelves formed in the first place. They are primarily the result of three processes. Sometimes, tectonic forces cause a part of the continent to sink or submerge. Other times, the land stays still, but global sea levels rise, flooding the edges of the continents, which happened extensively after the last ice age. Finally, massive amounts of sand, silt, and sediment carried by rivers and glaciers can build up along the coast over millions of years, extending the shelf outward. Because continental shelves are heavily influenced by the land next to them, we can categorize them based on the type of sediments they receive. For instance, glaciated shelves, like those around Greenland, are carved and covered by glacial debris. In tropical waters, like off Queensland, Australia, we find coral reef shelves built by biological activity. We also see shelves built by massive sediment dumps from large rivers, like the Nile, shelves carved by branching dendritic river valleys like the Hudson, and narrow shelves formed alongside young, active mountain ranges, such as those around the Hawaiian Islands. The size of a continental shelf can vary wildly depending on where you are in the world. On average, they are about 70 to 80 kilometers wide, with depths ranging from a shallow 30 meters down to 600 meters. The eastern coast of the USA has a broad shelf up to 300 kilometers wide, but the absolute largest is the Siberian shelf in the Arctic Ocean, stretching a massive 1,500 kilometers from the coast. Conversely, if you visit the coast of Chile, the shelf is almost non-existent because it sits on a convergent tectonic boundary where the ocean floor is being pushed under the continent. Despite being a small fraction of the ocean, continental shelves are incredibly important to human civilization. Because they are shallow and sunlit, they are bursting with marine life, providing almost all of the world's marine food and hosting the richest fishing grounds, like the famous Grand Banks. Economically, they are also powerhouses. About 20% of global petroleum and natural gas is extracted from these shelves, and they are prime locations for mining valuable placer deposits and phosphorites. Moving past the shelf break, we plunge down the continental slope. This is a much steeper region, with a gradient between 2 and 5 degrees, dropping to depths of up to 3,000 meters. This slope acts as the massive retaining wall of the continent, connecting the shallow shelf to the deep ocean basins. Geologically speaking, the bottom of the continental slope marks the true, final boundary of the continental landmass. Because of the steep drop, this area is often scarred by deep underwater canyons and trenches. As we reach the bottom of this steep continental slope, the angle begins to level out. This transitional zone is called the continental rise. It has a very gentle gradient, usually between 0.5 degree and 1 degree. Think of it as a massive wedge of sediment that has tumbled down the slope over millions of years and piled up at the bottom. As you travel further out, this rise becomes flatter and flatter until it seamlessly merges with the deep ocean floor.
Now we arrive at the deep sea plain, also known as the abyssal plain. These are the flattest, smoothest, and most featureless regions on the entire planet. Covering nearly 40% of the ocean floor, they sit at crushing depths of 3,000 to 6,000 meters. But why are they so flat? The actual rocky crust below is quite rugged, but over millions of years, a continuous rain of fine marine sediment and dressed dust has settled here, burying the rough topography under a thick, smooth blanket of mud.
Having covered the major zones, we now turn to the minor ocean relief features. Do not let the word minor fool you. These are some of the most dramatic geological structures on Earth. They include massive underwater mountain ranges called ridges, deep trenches, towering abyssal hills like seamounts and guyats, deep-cut canyons, volcanic island arcs, and biologically constructed atolls and reefs. Let us break these down one by one. First are the oceanic deeps, or trenches. These are steep-sided, narrow depressions that form the absolute deepest parts of the ocean, often plunging 3 to 5 kilometers deeper than the surrounding abyssal plain. Trenches are entirely tectonic in origin. They form at convergent boundaries, where one tectonic plate is being forced or subducted beneath another. Because of this violent crustal collision, trenches are highly active geological zones, closely associated with strong earthquakes and active volcanoes. You'll typically find these trenches lying along the fringes of the deep-sea plains, right at the base of continental slopes or curving alongside island arcs. They usually run parallel to fold mountains on the land. The vast majority of the world's trenches are located in the Pacific Ocean, forming the infamous Ring of Fire, followed by the Atlantic and Indian Oceans. The most famous of these is the Mariana Trench near the Guam Islands, which reaches a staggering depth of over 11 kilometers. In stark contrast to trenches, we have mid-oceanic ridges. These form at divergent boundaries where tectonic plates are pulling apart and magma is rising to create new seafloor. A mid-oceanic ridge actually consists of 2 parallel mountain chains separated by a massive central rift valley. Stretching for an incredible 75,000 kilometers across the globe, this continuous underwater network is by far the largest mountain system on Earth. Some of these underwater peaks rise 2,500 meters from the seafloor, and a few are so tall they break the surface to form islands. Dotting the abyssal plains are abyssal hills, primarily in the form of seamounts and guyats. A seamount is a massive underwater mountain with a pointed summit, purely volcanic in origin. They can tower 3,000 to 4,500 meters tall without ever breaking the ocean surface. The Emperor Seamount chain near Hawaii is a perfect example. A guyot is simply a seamount that once reached the surface, had its top eroded flat by waves, and then sank back beneath the ocean. Both are incredibly common in the Pacific Ocean. Next, we have submarine canyons. Just as rivers carve canyons on land, underwater currents laden with heavy river sediments carve massive, deep valleys into the continental shelves and slopes. These submarine canyons act as massive chutes, funneling sand and mud from the shallow coasts all the way down to the deep abyssal plains. Interestingly, because the underwater environment supports massive sediment flows, submarine canyons can be far larger and deeper than the grandest canyons we see on land. Submarine canyons generally fall into 3 categories. First, there are small gorges that start right at the edge of the continental shelf and cut down the slope, like the oceanographer canyons. Second, some canyons begin directly at the mouth of a major river and carve a path all the way across the shelf, like the Indus canyons. Third, some have a complex branching dendritic pattern deeply cut into the shelf edge, like those off Southern California. The Hudson Canyon is perhaps the most famous, while the absolute largest are found in the Bering Sea off Alaska. Moving to biologically formed features, we find atolls. These are low-lying islands found exclusively in warm tropical oceans. An atoll is essentially a ring of coral reefs that surrounds a central depression. This central area is usually a lagoon. Depending on the specific geography of the atoll, this lagoon might be open to the surrounding sea, or it might be completely enclosed, containing fresh, brackish, or highly saline water. Finally, we have features formed by a mix of erosion, deposition, and biology on top of existing underwater elevations, banks, shoals, and reefs. A bank is a flat-topped elevation found along the continental margins. The water here is shallow, but generally deep enough that ships can navigate safely over them. Because nutrient-rich waters well up around these shallow plateaus, banks are home to some of the most productive fisheries on the planet, such as the Dogger Bank in the North Sea and the Grand Bank off Newfoundland. A shoal, on the other hand, is a detached elevation where the water becomes extremely shallow. Unlike banks, shoals often project out of the water or sit just inches below the surface. Because they are so shallow and can shift with ocean currents, shoals represent a major hazard to maritime navigation, and sailors must carefully map and avoid them. Lastly, we have reefs. A reef is a rocky elevation or mound created predominantly by organic deposits, specifically the calcium carbonate skeletons of living and dead marine organisms like coral. They are a defining characteristic of the Pacific Ocean, often growing on the flanks of sinking seamounts and guyots. The largest and most famous is the Great Barrier Reef off the coast of Australia. Like shoals, reefs often extend near or above the surface, making them dangerous for ships. These stationary physical features of the ocean floor set the stage for the dynamic forces of the water itself, which we will explore next. Continuing our discussion on global circulation patterns, let us examine the specific currents of the Pacific Ocean. Under the influence of the tropical easterlies, or trade winds, the north and south equatorial currents travel a massive 14,500 kilometers from the west coast of Central America towards Indonesia and Australia. This constant flow actually piles up water in the western Pacific, raising the sea level by a few centimeters. Because of this pileup and the calm region of the doldrums near the equator, a counter-equatorial current flows backward from west to east, right between them. This exact mechanism was tested in the 2015 UPSC prelims. The question asked what explains the eastward flow of the equatorial countercurrent. While the Earth's rotation creates the Coriolis force, that does not cause countercurrents. Convergence is a prerequisite, but it does not always cause them. Salinity mostly affects vertical movement. The correct answer is the occurrence of the belt of calm near the equator, known as the doldrums, which facilitates this backward movement of water. As the north equatorial current hits the Philippines, it turns north to form the warm Kuroshio current. Meanwhile, from the north, the cold Ueyashio and Akats currents flow down past the Kamchatka Peninsula and Japan. Where these warm and cold currents meet creates one of the world's richest fishing grounds. The Kuroshio then moves east under the influence of the westerlies as the North Pacific Current. When it hits North America, it bifurcates. The warm Alaska current goes north, and the cold Californian current goes south, completing the gyre. In the southern hemisphere, the pattern mirrors the north. The south equatorial current turns southwards as the warm East Australian current. It eventually meets the eastward flowing South Pacific Current near Tasmania. As this water reaches the southwestern coast of South America, it turns northward as the cold Peru or Humboldt current. This cold current eventually feeds back into the south equatorial current. The zone where the cold Peru current meets warm equatorial waters is another highly productive fishing zone. Now let us cross over into the Atlantic Ocean. Similar to the Pacific, easterly trade winds drive the equatorial currents westward. The south equatorial current splits near Brazil, with a portion entering the Caribbean Sea. This water, along with the Antilles current, which passes east of the West Indies, flows out through the Strait of Florida. This combined flow becomes the famous Gulf Stream, a powerful warm current that travels up the eastern coast of the United States. As the Gulf Stream continues north near Newfoundland, it meets the cold Labrador and East Greenland currents flowing down from the Arctic. The confluence of these hot and cold waters produces famous dense fogs. More importantly, this mixing creates the Grand Banks, one of the most vital and richest fishing grounds on Earth. From here, under the influence of the westerlies, the water moves eastward across the Atlantic as the North Atlantic Drift. When the North Atlantic Drift reaches the eastern part of the ocean, it splits. The northern branch becomes the warm Norwegian current. This is incredibly important because it keeps the ocean north of Norway partly free from ice, allowing Russia to move cargo through the Barents Sea even in summer. The southern branch flows down between Spain and the Azores as the cold Canary current, which eventually rejoins the equatorial currents to complete the circuit. Trapped inside this massive North Atlantic gyre is a fascinating geographical feature, the Sargasso Sea. It is the only sea on Earth that doesn't have a coastline. Instead, it is entirely bounded by ocean currents, the Gulf Stream to the west, the North Atlantic Current to the north, the Canary Current to the east, and the Equatorial Current to the south. These currents deposit large quantities of marine plants, specifically sargassum seaweed, into this calm central region. Looking at the South Atlantic, the South Equatorial Current splits near Brazil. The southern branch forms the warm Brazil Current, flowing down the South American coast. Due to the westerlies, it swings eastward and meets the cold Falkland Current and the west wind drift. As this drift hits the southern tip of Africa, a branch flows up the western coast of South Africa as the cold Benguela Current, completing the South Atlantic Circuit. The Indian Ocean is unique because it is essentially half an ocean, blocked by the Asian landmass to the north. Because of this, its northern currents are heavily dictated by the seasonal monsoon winds.
During winter, the northeast monsoons drive the water in the Bay of Bengal and the Arabian Sea in an anti-clockwise direction. The standard north and south equatorial currents flow westward, creating a standard equatorial countercurrent flowing eastward between them.
But in the summer, everything changes. The strong southwest monsoon winds completely obliterate the north equatorial current. Instead, a strong current flows from west to east. Because the westward flow is destroyed, there is no counter-equatorial current during the summer either. The entire water circulation in the northern part of the Indian Ocean reverses to a clockwise direction. This seasonal reversal is a defining characteristic of the Indian Ocean.
The southern half of the Indian Ocean behaves more like the Atlantic and Pacific, as it is less affected by the monsoons. The south equatorial current flows west and splits around Madagascar into the Mozambique and Agulhas currents. These warm currents merge at the southern tip and eventually meet the west wind drift. A branch of this cold drift turns north along Australia's west coast, forming the cold West Australian current, which feeds back into the equatorial flow.
Now let us discuss the profound effects these currents have on our planet, starting with desert formation. Major hot deserts like the Sahara, Atacama, or the Great Australian Desert are often located on the western sides of continents, between 20 and 30 degrees latitude. This is largely due to cold ocean currents. These cold currents chill the oncoming air, causing a temperature inversion that inhibits convection. This desiccating effect means the air loses its moisture as fog over the ocean, leaving very little rain for the adjacent land. Furthermore, these deserts lie in the subtropical high-pressure belts, where air is descending, which is a condition least favorable for precipitation. The trade winds here blow offshore, meaning they blow from the land toward the sea, carrying moisture away. Any wind that does reach the desert is blowing from cooler to warmer regions. As the air warms, its relative humidity drops, making condensation almost impossible. Under these harsh conditions, every bit of available moisture simply evaporates. Conversely, warm ocean currents bring rain to coastal areas and even deep into the interior. For example, the warm North Atlantic drift is responsible for the summer rainfall and milder British-type climate. Warm currents flow parallel to the east coasts in subtropical latitudes, creating warm, rainy climates. Additionally, these currents pile up massive amounts of warm water in the tropics, providing the immense thermal energy required to fuel tropical cyclones. The mixing zones of cold and warm currents are the richest fishing grounds globally, like the Grand Banks or the coast of Japan. This mixing replenishes oxygen and promotes the growth of plankton, the primary food for the fish population. Currents also moderate coastal climates, bringing warmth to high latitudes like England, or a cooling effect to places like Spain. Furthermore, these mixing zones create persistent foggy weather, where precipitation often occurs in the form of drizzle. It is important to distinguish between ocean currents and water masses, a topic covered in the 2019 UPSC mains. While ocean currents are relatively rapid surface movements that influence sea surface temperatures, a water mass is a massive body of water with distinct physical properties, like temperature, salinity, and density, formed by its history. For instance, dense cold water from melting polar ice sinks and moves slowly along the ocean floor as part of the global thermohaline circulation. While surface currents heavily influence coastal climates, water masses are crucial for the deep ocean, or benthic zone. They deliver vital oxygen to deep water habitats. Where these water masses rise to the surface, a process called upwelling, they bring cold, nutrient-rich waters that support massive marine ecosystems. Conversely, downwelling regions tend to have lower productivity because nutrients are not continuously replenished from below. The movement of these masses can even impact sensitive ecosystems like coral reefs. Finally, let us look at navigation. The flow of a current is referred to as its drift. Surface currents can be quite fast, reaching speeds over 5 knots, or about 9 kilometers per hour. Historically, ships heavily relied on these currents and winds to cross the oceans. For example, sailing from Mexico to the Philippines utilized the North Equatorial Drift. While modern propeller-driven ships are less dependent on them, utilizing favorable currents still saves significant time and fuel. To wrap up our discussion on currents, consider this 2002 prelims question. It asks which statements about ocean currents are correct. We know they maintain heat balance, are driven by winds, and are shaped by ocean configurations. But are they always slow surface movements? No. As we just learned, they can reach up to 9 kilometers per hour, and cold currents often flow below the surface. Therefore, statement 1 is incorrect, making the right answer 2, 3, and 4.
This continuous flow of water is just one way the ocean moves. Next, we will examine the vertical movements driven by celestial bodies, known as tides. Let's examine how the magnitude of tides changes based on orbital distances, starting with the Moon. The Moon's orbit around the Earth is not a perfect circle, it's an ellipse. Once a month, the Moon reaches its closest point to Earth, known as perigee. Because gravitational pull strengthens as distance decreases, the tidal range during perigee is much greater than normal, resulting in unusually high and low tides. Conversely, 2 weeks later, the Moon reaches apogee, its farthest point from Earth. At this distance, the Moon's gravitational force is weaker, meaning the tidal ranges are noticeably less than their average heights. Just as the Moon's distance varies, so does the Earth's distance from the Sun. When the Earth is at perihelion, which is its closest approach to the Sun around January 3rd each year, the Sun's gravitational pull on our oceans is maximized. This leads to much greater tidal ranges, giving us unusually high and low tides. On the other hand, when the Earth is at aphelion, its farthest point from the Sun around July 4th, the solar gravitational influence is minimized, resulting in tidal ranges that are much less than average. Because tides are driven by the predictable orbits of the Earth, Moon, and Sun, we can forecast them with great accuracy. This predictability is a massive advantage for navigation. Many major harbors are located within river estuaries that have shallow sandbars at their entrances. During low tide, large ships simply cannot pass through. But during high tide, the water level rises significantly, allowing deep draft ocean-going vessels to enter safely. Famous examples of this include the Port of London on the Thames River and the Haldia Port in Kolkata on the Hooghly River, both of which rely heavily on these tidal swells. Tides do much more than just move ships. The massive kinetic energy of moving water can be harnessed to generate electricity. Countries like Canada, France, and China use tidal power, and in India, a 3-megawatt tidal power project was built in the Sundarbans. Ecologically, tides act like a giant pump for estuaries. As tidal currents move seawater in and out, they circulate vital nutrients and oxygen, flush out polluted water, and prevent excessive silt buildup. Furthermore, fishermen rely on high tides because rising waters bring large schools of fish much closer to the shore, making for an easier and more abundant catch. Let's apply what we've just covered to a past EPSC prelims question. It asks us to evaluate 4 statements about tides. Statement 1 is correct. We know tides aid navigation and fishing. Statement 2 is also correct, as high tides raise water levels for large ships. Statement 3 is true. The ebb and flow of tidal currents naturally desilt harbors. Finally, Statement 4 is correct, because both Kandla and Gujarat and Diamond Harbor in Kolkata are indeed major tidal ports in India. Therefore, the correct answer is D. All 4 statements are true. While gravity pulls the water vertically, the actual height of a tide at a specific beach is largely determined by horizontal forces, specifically how the water interacts with the land. When a tidal bulge rolls into a wide, shallow continental shelf, the land acts as a barrier. The water has nowhere to go but up, resulting in a much greater tidal height. In contrast, if a tidal bulge hits a steep mid-oceanic island, there is no shallow shelf to act as a barrier, so the water simply flows around it, keeping the local tidal height relatively low. The shape of the coastline plays a massive role in tidal magnitude through something called the funneling effect. When a massive volume of ocean water is forced into a bay or estuary that narrows as it goes inland, that water is squeezed. Because it cannot spread out horizontally, it is forced upward, drastically magnifying the intensity and height of the tide. The most famous example of this is the Bay of Fundy in Nova Scotia, Canada. Its unique funnel shape creates the highest tidal range in the world, with water levels fluctuating by an astonishing 15 to 16 meters between high and low tide. Sometimes the funneling effect creates a spectacular and violent phenomenon known as a tidal bore. When a strong incoming flood tide enters a narrow and shallow river estuary, it meets the river water flowing in the opposite direction. The friction of the shallow riverbed and the clash of opposing waters cause the front of the tidal wave to pile up vertically. This creates a steep wall of water that literally rushes upstream against the river's current. It's called a bore because of the loud roaring sound the water makes as it tears through the narrow channel. Tidal bores are relatively rare because they require a very large tidal range, usually greater than 6 meters, to form. You can find them in specific locations globally. In India, they are common in the Hooghly River. The Chantong River in China is famous for hosting the largest and most powerful tidal bores in the world. Interestingly, the Amazon River also experiences strong tidal bores.
Even though the mouth of the Amazon is incredibly wide, which usually prevents spores, the river is so shallow and choked with low-lying islands and sandbars that it creates the necessary friction and funneling to generate a massive bore. Unlike regular tides, which rise and fall gently and predictably, tidal bores are sudden, violent, and highly dangerous. They pose a severe threat to shipping and navigation in estuarine zones, as the rushing wall of water can easily capsize boats and even larger ships caught unaware. Beyond human impact, tidal bores are ecologically destructive. The violent churning of the water kicks up massive amounts of silt, which can bury and kill bottom-dwelling marine life. Because of this, you will often see flocks of scavenging birds following right behind a tidal bore, feeding on the disrupted and injured marine life. To wrap up our comprehensive look at tides, remember that these rhythmic rises and falls are primarily driven by the gravitational dance between the Earth, Moon, and Sun. The magnitude of these tides constantly shifts based on orbital distances and alignments, giving us spring, neap, perigean, and apogean tides. However, the actual height of the water you see at the beach is dictated by the shape of the coastline through barrier and funneling effects. Ultimately, understanding tides isn't just an academic exercise. It is absolutely crucial for global navigation, maintaining healthy coastal ecosystems, supporting fishing industries, and even generating renewable energy.